It's been a while since our last data science project video here on the channel, but for good reason. I've been really focusing on building out a statistics playlist. And well, today we're going to be taking a look at more of a stats focused video. What we're going to be doing is analyzing one of my favorite hobbies, which is running. And last month I ran my first 100 miler, Tampa 100, and I got this belt buckle. And yeah, my bib is kind of trashed over here, but I thought it'd be really fun to take a look at some of the different types of t-tests and z-tests and ANOVA based off of the data set of 2023 and 2024 results on this race. Unfortunately, since this is only the second year of this race, there isn't a lot of historical data, but we can still compare competitors from year to year that ran both years. We can take a look at times and much more. So this video is also going to encompass a little bit of EDA. We'll be taking a look at some basic statistics, making some graphs, and much more. So if you're here to learn and have some fun with a beginner level data science project, this video is for you. So let's jump through some of the data. All right, so let me show you guys where I'm going to source the data for this video. So here's a website called UltraSignup, and UltraSignup essentially hosts all these different types of ultra running events and stores their data. What's kind of interesting, I believe there's a Kaggle data set that scrapes a lot of the UltraSignup races and populates it. I'm not going to use that Kaggle data set for this video just because I'm only going to look at the 2 years of the Tampa Bay 100, 2023 and 2024. And it's pretty easy to grab the data on here. So all I do, I'm just going to the results on here and I'm literally just copying this, like grabbing all this information, and then I just threw it into a Google sheet. So I have 2024 over here and then 2023. I did clean up parts of the data. So just to show you guys, right? This doesn't have state labeled, so I put state on there. I removed rank. Rank is essentially a score that UltraSignup puts towards your time on the event. I don't know how this rank is calculated specifically, so I'm not going to use that. At the same time, there's this DP, which is for division place. Again, I'm not going to use that for this video. And then, right, all these results over here, I removed that as well. But you can just see like historical running events for someone. So just to show you guys where I'm at on here, right, there's 41 finishers. I believe the race originally capped at like 100 people. Not everyone shows up on race day, so I don't believe everyone is put in over here. And then if you do not finish the race, you get assigned a time of 0. So over here, right, 0 is did not finish. That's how I marked it. And we'll go through this a little bit later in the video, kind of why I did not finish. You'll see my code. But regardless, I'd rather put do not finish than it's 0 on this side of things. And you can see like 35 people didn't finish in comparison to 41 that did. I mean, these races are tough, right? People struggle running a marathon. This is 4 marathons in a row. Plus, you have to deal with the heat overnight. I could talk a lot about it. But yeah, so I finished right over here, kind of middle of the pack, which I'm okay with that. 32 hours. Going into this race, I really wanted to do 24, but man, I struggled towards the end. I was going 30-minute miles, and it was pretty bad. A lot of people passed me at the very end, right? If you're essentially walking at the end of the race at 30-minute miles and someone's waddling at 15 to 20 minutes, you're going to get passed. And you can see there's a good chunk of people at 30 hours. Like if you ran sub 30 hours, you're top 15 in this race, which is impressive again, because you're close to 100 people that start these type of races. And to mention, every 100 miler is different, even year to year. And this race this year was kind of hot. In November, it got up to over 90 degrees in comparison to the year before. At least talking to a few people that were helping out at the event and like pacing and things like that. But regardless, we're going to run a lot of statistical tests based off of 23 and 24. It's going to be a pretty fun video. I am going to give you guys the link to this over here so that way you guys can download it. I'm going to use a Google Colab notebook and we'll go through every single cell line by line. I do wish there was more years of data, but this race just started a few years ago, right? 2023. So not a lot of historical data associated with it, but that's kind of that. And yeah, so if you're an ultra runner, awesome. If not, well, welcome to the sport. You're going to learn a little bit in this video. Tampa Bay 100 over here. Really fun race, man. It was, this was difficult. I don't know if I'm in any of these pictures or not, but regardless, yeah, let's jump into some coding. All right, this is Google Colab. If you've never used Colab before, highly suggest that you take a look at it. You can run one cell at a time, and it's really good for data analysis. Okay, and real quick, also to mention, I'm not doing random sampling throughout this video. As mentioned, there's 2 years worth of data for this Ultra event. Only about 40 people finish each year. So give or take, there's like 80 runners, probably a little bit less, that have completed this course. So not a ton of data out there. So be warned on that. So regardless, let's start by adding in a bunch of our different dependencies. So we're going to start off with pandas. So import pandas as PD and import numpy as NP. And then from stats models.stats.weight stats, import our z-tests. From scipy.stats, we use that a ton in the series. Import skew, f one way, Pearson r, t test, rel, chi, square contingency. Hopefully I spell everything correctly. Spearman r, Levine, Shapiro. I think that's it. Let me just double check. Oh, Kruskal. And Kruskal. And then next, we are going to plot a few things in the beginning. Import Seaborn as SNS. And then import matplotlib.pyplot as PLT. Man, that's a lot already starting off this video. And I have examples of all of this on the channel. So if you're not familiar with any of these imports, check out some of the other videos. Specifically for this one, check out the statistics series. So feel free to label these if you want. There's text right here, but I am just going to use comments. That's what I like doing best. And moving forward. So what we're going to do first is import in the spreadsheet. And so here's how you do this. You see this folder icon over here. All you have to do is drag in your spreadsheet. Okay, so once you have your spreadsheet, which I'm just going to grab mine really quick, all you have to do is drag it in. I believe this is the correct one, if I remember correctly. Actually, it is not one of these two. I think it's this one right over here. Having both these named, it's probably the same data anyways. Okay, so now what we're going to do is we're going to grab the file path for it. So all you have to do is click these 3 dots, and then you're going to click copy path. And then click this X to close out. And we're going to say is file path equals, and then we're going to put in single quotes and paste, right? /content /Tampa 100, right? We still have a little bit of work to do. So what we're going to do is we're going to split up our data 2024 versus 2023. So I'm going to say data 2024 equals pd.read Excel. So read Excel, which I don't use as much as CSVs since I use CSVs a ton, but we're going to have our file path in here, and then you specify the sheet. So sheet name, and then call it as 2024. So 2024, like that. Now we have our 2024 data. And guess what? You can just copy and paste because we're doing the same thing for 2023. Why type it all out again? Unless you just want to memorize it. And boom, we have both years over here. And just to show you that this is working correctly, let's just print out, or not even print out, we can just call our head over here. So data 2024.head, we'll do 5. And you can see place, first name, last name, city, state, age, gender, and time. All right, so now let's do the same thing for 2023. And there we go. Place, first name, last name, city, state, age, gender, and time. Great. Now, here's the fun part. And as the most views on the channel, data cleanup. I did do so much data cleanup at work. It's always fun, although I'm doing more SQL data cleanup than Python. But regardless, there's always some sort of data cleanup. So the first data cleanup side I want to do is I want to get rid of first name and last name. Let's combine them and have it as a full name. One thing we're going to do is we're going to compare people that have ran in both years, 2023 and 2024, and compare their times. Now, also there's a contingency. The runner has to have both races completed. That way they have a finish time. There may have actually been some runners that have done both years, but I'm only looking at finishers. So let's combine these first and last names. So what we have to do is apply this to both data frames. So I'm going to start off with data 2024, and we'll call this new column full name. And all you have to do on the Python Panda side of things, if you are new to it, call your data frame here, create a new column like that. Super easy. So we're going to say this is equal to data 2024, and then grab your first name. So first name, then what we're going to say is plus, and we're going to have a space, right? That's just space, and then plus, and then we're going to just copy this because I don't want to write data 2024 again in name, and just change first name to last name. And this is going to create that brand new column. Now duplicate this for 2023, right? And just go over here like this, 2023, 2023, 2023, and done. Okay. And now we can check both of these heads if you want. I probably am only going to look at 2024. So put head, and we'll say 5. And check this out. For place, first name, last name, city, state, age, gender, time. And now we have full name. Great. And after this, what we're going to do is we're going to drop our first name and last name because we don't need it anymore, right? So what we're going to say is data 2024. We're going to say dot drop, and then we're going to put in our columns that we want to drop. So first name, like that, and then comma, and we'll do last name also. So last name like this. Then specify the axis. So axis equals 1, and then we'll say in place equals true. For both of those. Okay, and then just the double check name on here. Say data 2024.head 10. And check it out. Now we have place, city, state, age, gender, time, as well as full name. Okay, so our next step on the data cleanup side of things is we're going to separate our data frames. So part 2 is we're going to make 4 data frames. So 4 different data frames. Sounds weird at first, but we'll need it a little bit later in the video. So what we're going to take a look at specifically is if someone finished or not, and it's going to help with our data cleanup, because if you don't finish, you don't have a time, right? And one of our columns is going to be time. So you have DNF on there. And if we just had zeros, well, that's kind of annoying. So what we're going to look at first is did not finish, right? Just to show you how this looks. So data 2023. And then over here, we'll data 2023. Then we'll look specifically at the time column. And this is going to be equal to did not finish, did not finish. And we're just going to do a head of 5, head 5. And just to show you, right? Place, city, state, age, gender, and full name over there. So that's what we're going to be basing this off of. And let's start this off. So what we're going to do is data 2023. We'll say finishers. And this is going to be equal to data and then 2023. Inside over here, we're going to have data 2023 again. So data 2023. Let me scroll up a little bit. And we'll have over here time. And we're going to say this is not equal to did not finish, did not finish. And we're going to make a copy. So copy. Otherwise, we're going to get some errors. And that's good there. Now I'm going to duplicate this for 2024. So just change all your 3s into 4s, and that should impact only a few spots. 1, 2, 3. Right. And then what we're going to do next is our DNFs. So I'm just going to copy this code again. We're going to put in here, instead of finishers, use the classic DNF, right? And we're going to say this is equal to, right? Did not finish. That's our DNF. And then we'll do the same thing for 2024. So we'll put 2024 here, 2024, 2024, 2024, and we are set. Great. Now, part 3, and we'll go over these data frames later, but we'll go part 3. We're going to drop features for DNF. They don't have a time, right? So we don't need that. So what we'll do is grab the name, so data 2023 DNF, like that. Then we're going to say .drop, and inside over here, we'll again specify our columns. The first one is going to be place, because there is no place if you don't finish, right? Every DNF, you don't have a ranking. So we don't need the place, and then we also don't need the time. So they're out the door. Then we'll say axis equals 1 again, so axis equals 1. And then we'll say in place equals true, in place equals true. And there we go. And we'll just do the same thing for 2024, right? So 2024, done. Great. And then part 4, we're going to convert our time. So part 4 is going to convert time into minutes. And this is only going to do the finishers, right? Or only be the finishers, because DNF, you have no time. So we'll say is data 2024 finishers. Thank you for the completion. Well, we probably should start with 2023 since we're doing that for the other ones. We'll grab the time column. We'll say time. We're going to say this is equal to, and we'll have our time once again. And then we'll do as type, and then we're going to specify this is going to be a string. Right? Just follow along, and we'll do the same thing for 2024. So grab 24 like that, and I'm going to run both these cells at the same time. Okay. Next, what we want to do is convert to a time delta. So we'll say convert to time delta, and what we'll have on here, and I'm just going to grab this, and we're going to say it's a new column. We'll call it time delta. We're going to drop it at the end, so don't worry too much. We're going to say this is equal to pd.to, and then time delta, and then we'll have our data finishers like this. So data 2023 finishers time, and then put errors, of course, like that. And we'll do the same thing for 2024. Just change our few 2024 spots. Great, both of those are here. And lastly, let's convert this to minutes. So convert to minutes. And all you have to do on that side of things is, and we'll start with 2023. We'll call this race minutes. So race minutes equals, and we have over here our time delta. So we'll grab that. And then all we have to do on here is .dt .total seconds. And then it needs to be like that, divided by 60, right? 60 seconds in a minute. We'll do the same thing for 2024. So grab that. Have that there. Have that there. And then now we would just want to drop our last columns. So over here, we want to keep the time, that's fine, but we'll drop our time delta because we don't need that anymore. And all you have to do, grab all this again, right? Go down here, data 2023, and it should be finishers. I grabbed the wrong one. And I'll just put over here, drop time delta, right? And change it to 2023. Where's our time delta? And we'll do the same thing for 2023. I'll put 2023 above it. And lastly, what we should do is print out a head. So it doesn't matter what year, just put over head 5 just to make sure that this was working correctly. So you see place, city, state, age, gender, time, and then you see the race minutes in over here. And 18, right? So let me throw up a calculator and just to do some very quick math, right? Just to make sure it's done. And yeah, I mean, you can do mental math, but 18 times 60, right? And then we plus 33. You can see 1113, 1113. So, and 0.1 because this guy has 6 seconds here at the very end. And yeah, so great. Our conversion has worked properly. Again, we can keep time in here because I do think it is helpful, but we didn't really need time delta. So now we're going to move on to our next section, which is going to be taking a look at some basic stats off of these data frames. Then we'll jump into some plotting. So if you want to take a small break, this is probably a good spot to do that, and then come right back to the video. So let's start off finding our average, median, and standard deviation. So we'll say average, median, and STD, and let's get started. And we'll start off with the mean, and this is pretty easy. So we'll say data 2023 finishers. We'll go race minutes, and we'll just grab the mean. So mean, and you'll see in 2023, 1726 minutes, which if you throw out the calc, 1726 divided by 60, almost 29 hours. And then if we go to 2024, grab that, you can see is 1809. If we do 1809 divided by 60, 30.15. So now let's take a look at the median side of things, because there's a lot of things that can impact the mean, right? You have faster runners that are going to run under 19-20 hours, and it could skew our mean. But then you also have slow runners that are going to be super close to the end time of the race, which I think was like either 36 or 38 hours. I can't remember. So let's see how much our median differs from our mean. And we'll also be taking a look at skewness a little bit later. So a little bit of hint there. But regardless, this is going to be very similar code, right? All you have to do is change mean to median. So we'll do that. And just good information to know when plotting also. So the median is 1732, which is actually really close to the mean in 2023. And in 2024, it's 1865, which you throw this out over here, 1865 divided by 60, you're looking at 31 hours. Again, a little bit faster than where I was at, but yeah, so that's our median. And then let's take a look at our standard deviation. So we'll put STD here. And again, going to be essentially the same code. Just grab STD. We'll do this for both of them, right? STD, and then also STD, run that. You'll see 272, which is a lot, right? 4.5 hours standard deviation. And then over here, 247. So 2024, a little bit smaller standard deviation than 2023. Also makes a little sense. First year, no one really knows what the course is like. Second year, people do. Although there wasn't a lot of people that ran both. Let's take a look at finish rates. So again, I don't know if all the do not starts are in this data set or not. I assume it's just people that attempted the race and didn't finish. Every race is a little bit different on UltraSignup with like how they specify it did not start. Originally, there was supposed to be, like I said, about 100 people that signed up for each of these, and then obviously that didn't show up in the data set. So I assume that either people dropped before the race, they didn't have enough people to show up on race day. The races were sold out, so it was just people not being able to sign up in time, or people signed up and just never showed up to the start line. So regardless, we're going to just take a look at a finish rates of what's going to be in the data frame, right? everyone that showed up in UltraSignup. So again, I think it's everyone that actually showed up. So we'll take a look at on here is we'll say data 2023 finishers, and we'll grab our full name and we'll do a count. So full name like that. And then we'll say count. And then what we'll do is divided by, and we're going to add two things. So first is we're going to add this count, and then we're going to add in our DNF on this side of things. Yeah, so we're going to add in our DNF. So we'll say plus, and then throw in our DNF over here. So this is getting in the way a little bit. DNF like that. And you can see it says 65% or 65.7% completion rate in the inaugural year, 2023. I'm curious what 2024 looks like. Again, 2024 was a harder race, and you can see 53.9%. Next, let's take a look at some of the top cities of people that ran in this race. So we'll take a look at top cities. And let's look at that. So all we want to do on here is we don't even have to do our finishers. We can just look at data 2023. We'll grab our states. So states, and we'll do some value counts, right? Because it doesn't matter if you finish or you didn't, right? We're just taking a look at who signed up. So we'll say value counts over here. And let's take a look at the top 5. So we'll say head and 5. And they should all be in Florida, I would assume. Well, I looked at states first, but Florida, 59, which is a lot. Then you have USA. Again, people that just had like an anonymous address. I assume North Carolina 2, Alabama 2, and then there's probably a bunch with 1. Let's also take a look at cities for 2023, which I think I said the first time rather than state. So I apologize there. Cities, Tampa, I mean, it's the Tampa 100, Clearwater, which is literally on the route, Odessa, Palmetto, which Palmetto is really far away. Odessa is a suburb of Tampa, so pretty close by, although it's not on the course, and Orlando. And I've lived in 2 of these cities. I grew up in Odessa, and I live in Orlando, so it's pretty cool. We'll jump into 2024 now, and do that. So data 2024 states. Again, Florida should dominate this. And Florida 56, Virginia showed up 3, Georgia 2, North Carolina 2, Ohio 2. I ran with one of the Ohio runners, and probably first, or not first, but probably about 10 or 15 miles I ran with them. But regardless, we'll jump into city. Grab that now. And for city purposes, Tampa, again, no surprise. Clearwater. Ocala has a pretty big running scene. There's 3 over there. Virginia Beach. So the Virginia runners, there's 3. Probably came from the same city, knew each other. And then Plant City, most famous for their Strawberry Festival in Florida. Okay, I think we are good to start taking a look at some plots. So again, if you want to take a break, go and do that. Otherwise, we're going to jump into the plotting section. All right, so let's start plotting some stuff. Nothing to be too crazy on the plot side of things, the plotting side of things. But let's get going. Now, first thing I'm going to do is plot male versus female runners. Female runners. And we can just do this in a line of code. And, you know, there's a lot more things that we could customize on it, but at the end of the day, just a quick project. We're going to do data 2024. We're going to say x equals gender. And we could have easily done this from what we did for value counts, but we're starting off some basic plots, right? And you can see there's quite a few more males running this race than females. We can do the same thing for 2023. And looking at 2024, right, probably a little bit under 20 on that side of things. And, you know, a little bit more, maybe 25, 26 in 2023. And what we can do now, this one is take a look at some of the distributions. So distribution of time, right? And running is interesting because depending on the event that you run, you could have separate distributions between males and females. Ultra running is an event where the elite females could beat elite males. One of the best ultra runners out there is Courtney Water. She runs 100-mile, 200-mile races and beats everyone in the competition. It's one of those sports where it's kind of equalized once you get over a certain amount of time running. So again, it depends on the type of race and different things like that, race environments. But typically in ultra running, you see the times a lot closer than you would in other running events. So I'm not going to separate the distribution at first. I'll show you how we can separate this in a little bit later, but let's start off with that side of things. So what we can do is sns.displot, and we'll start off with 2023, right? So I'll say data 2023, and we'll look at finishers, right? And we're going to plot the race minutes. So race minutes like that. And then we're also going to add in a KDE, right? Just expanding on a little bit more than we did in the last one, right? This one, super basic displot, we'll add on. So we'll throw the KDE over here. And you can see this is kind of skewed. It almost looks like we have some runners over here that are better. And then we have the rest of the field on this side of things. And let's take a look how 2024 looks like. So I'm going to just grab this here. And why I said this also is we had a peak, right? You kind of two values, you have a peak right there. And then you also have a peak right here. So like this could be a possible multimodal distribution, right? You have people over here that say not fully elite because while the race was tough, these aren't elite times. Some of the best ultra runners run 14, 15 hours. They would have done that in this race. But let's say you have people that are probably your top 5, top 10% ultra runners, and then you just have the normal field, right? You could separate those out. Let's look at 2024 and see how that looks. We have the same thing that's going on. And take a second and check this out. Again, you kind of have this peak right here. And in this race, it looked like it was probably around like 15 to 1600 minutes. And if you look over here, it's around 1400. And we talked a little bit about the differences in the median and mean, right? And it looked like it was like about like 100 difference. You can take a look. Median race difference, right? 1732 versus 1865, 1726, 1809. Like I said, this year was a lot hotter of a race than it was in 2023. Which slows down time when you're running 100 miles, right? Especially if you add in an extra 10 degrees. Less people are going to finish. You're going to run slower. It's just something that happens in running. And you can kind of see it with these charts, right? Like our peak on here is around 1800, but then our peaks on here, we have technically two peaks. We have one after 2000, and then we have one over here 1800, and then we have another peak. Oh, I should say three peaks. We have another one right over here. But again, you could separate this data if you really wanted to. Another video maybe. But what I wanted to look at is skew, right? And I am going to separate by gender to see if there makes a difference. But based off of what I was saying, it's probably the more experienced runners and people that have just better athletic ability versus, your average ultra marathoner. Which sounds weird to say, but like there's always someone that's gonna be better than you in most cases. So, all right. What I was gonna look at is the skew. So let me show you how we can do that. I know this is technically our charting section, but I feel like this is the best time to talk about skew. So we'll write this in here and let's get going with it. So we'll look at skew 2023. So 2023 equals skew. And then we'll look at data finishers 2023, which I'm just going to copy this over here and change it to 2023. We'll duplicate it for 24 also. And we'll look at race finishers. And we'll examine it, or race minutes, sorry. We'll examine the skew at the very end. So there's skew 2023. Now let's look at skew 2024. And we're going to probably get the same results on skew. Well, not the exact data points, but they both should be negative. And let's print these out. So print out skew 2023. We'll have that there. You see there's a negative value associated with it. And then it should be the same. 2024 was actually worse. We should see a lot more of a skew. So we should get more negative number. And negative 0.72 on that side of things. So what this negative number tells us is we have a longer tail on the left side of things, right? Makes sense. Less people are finishing faster, more people are finishing later in the race. And that's what the negative skew gives us, right? Obviously, few fast people that crushed this race, but overall, a lot of people struggled quite a bit and finished slower. So there's the skew. Back to what I was saying, let's attempt to look at gender and see if we can have a difference in our distributions and try to get normally distributed on that side of things. And let's try it. No promises though. So what we'll do is we'll separate all of these over here, right? So we'll have male finishers 23. Then we'll have, I'm just going to put all this in one cell. So typically I separate them, but that's all right. I'll just literally copy these here. Female, I put female instead of female. That's embarrassing, but female. All right, so, and we'll just write out one line and duplicate it. So data 2023 finishers. Inside over here, we're going to look at data. We'll say gender. We'll say this equals. Well, I think I have to put copy on the end of this one because we're taking a slice of that frame. Pretty sure. If not, I apologize for that mistake. We'll put 2024 here. And we'll do the same for male and female. All right, so 2023, F, and then F should be good here. Cool, no errors. All right, so we'll look first at the male finishers from 23. So what we'll do is sns.dispplot, and then we'll add in male finishers 23. Again, we're looking at race minutes, so race minutes like that. And then we'll set our KDE. So we'll say KDE true. Perfect. And let's see if this is better. And take a look at that. Way better of a distribution when we separated these. Obviously, there's some skewness, but it looks way better than what we had before. Hold on one second. I see a saving failed. I'm going to fix this real quick and we'll resume. All right. Anyways, we still see some of the faster times, but this looks already way better than what we had before. Let's see if we could do the same on the female finishers for 23. So female finishers and not as much. Now, also you have to factor in the sample size, right? So on the male side of things, and again, we had what? It was 80 people, or sorry, we're looking at finishers. It was 40 finishers for each race, right? We're specifically looking at the females, which there's a lot less female runners. If we go back up over here, right? Where is this at? You can see male versus female. You know, in 2024, which I plotted that here, there's only 20 female finishers. If they finish at the same rate as males, there might only be 10. Well, I guess we could technically count these too, right? This is the female finishers, right? So you can see 2, 5, 9, 14, 19. Wow, did all the female finishers almost complete the race? Oh, this is 23 still. 23 had what, 25? More than 25, like probably 27, 28. I'm like, man, did we almost get 100% finish rate from females? But regardless, again, we're skewed. We have some really fast runners over here. They're like a little bit over 20 hours, right? 1200 is going to be 20 hours. And then we have a lot more that finished a little bit later. Let's take a look at 2024 now. And let's see how that looks on the male side of things. So on the male side of things, this looks worse. Man, you had 2 runners that ran really fast. Then you had a good portion right over here, around let's say 1600 minutes. And the interesting thing, right? So if you have 1200 minutes, it's 20 hours. Another, what's probably happening is there's a good amount of people that tried for 24 hours, and they failed, but they finished slightly after. And then you can see this large group of people all over here on the male side of things. That didn't really work too much on this side for 2024, but that's all right. Let's see if we can put female on here. And this almost looks like a uniform distribution on the female side of things. You can see 3, 6, 8, and only 12 out of 20. Or I'm going to say 20. It's different, but 12 out of 20 finished. No one finished in this time period, which is interesting, but very close to uniform, right? If one of these finishers went a little bit faster, this is pretty close on that side of things. Obviously, there's no one that finished in this time frame over here. Again, if this race was, we had 5 or 10 years of data and we plotted it, it'd be interesting to see if it turned out to be uniform, or if we would have, something that's like left skewed, or what we would have in general. It'd be kind of interesting to look at in a few years, give or take. But again, with these races, it's going to be different every single year. So it's hard to compare year to year. Race courses also do change sometimes. This year's course is a little different than last year. Okay, so we took a look at just in general 2023 versus 2024. We looked at male versus female. Let's take a look at age. So this is going to be multiple box plots, and it's going to be a little bit more intensive on the coding side of things. So multiple box plots, and let's go for it. So what we're going to say is we're going to have combined data. So combined data equals, and we'll say pd.concat, well, pd.dataframe, and inside over here, we'll have, it should have been this. All right. And inside over here, we'll have age, and we'll go concat. So pd.concat, and we'll have over here is data 2024 finishers. We'll grab the age there. Then we'll look at the DNF. The same thing. DNF. And then we're just going to duplicate this again for 2023. So 2023 and 2023. Awesome. Then we'll have category next. So we'll say category, and inside over here, let's go through that and pull that out. So what we'll have on here is we'll start off with 2024 finishers, or say times the length, data 2024 finishers, age. Plus, and then we'll have 2024 DNF. Put DNF here. We'll say plus, and we'll do the same thing for 2023, right? So just label these 2023 across the board. Hopefully this code is correct. Nope, looks like I have an error. Let me see where my error is at. My data equals pd.dataframe. That looks like everything lined up on my side. Code, age, pd concat. Let's good there. Data 2024 finishers. All this should be good here. Close that out. Then, oh, that should, no, because this needs to be, well, that's giving my error. Nope, I still have another one, no data frame. The capital F. I made a lot of errors there. And we're good. All right, I'm fixing my errors. No space, remove that space. Messed up the capital F, and I had a plus at the very end. Apologize, but it happens when you're live coding. All right, fix all those. And then what we're going to do now is create a box plot. So we'll have over here plt.figure. We'll set fig size. So fig size equals 10.6. Then sns.boxplot data equals, and it's going to be this combined data that we have. Throw that in over here. X equals category. So category. And then y equals age. Y equals age. Then what we'll do is we'll add in our titles and labels. We're not going to be lazy like the first one. That was just a warm up. So plt title. Age. Distributions of finishers and DNF. DNFs 2023 and 2024. And then plt.xlabel, category, then plt ylabel, age, plt.xticks, rotation equals 45, plt.typeLayout, and plt.show. plt.show. Again, hoping no errors. And awesome. So what this shows is the distributions of all these different finishers and people that did not finish the race. And one thing that I noticed right away is the people that are older, typically DNF. And you can take a look at this side of things, right? Middle 50% right here is higher in 2024 and slightly higher in 2023. You can see in 2023, essentially everyone under the age of, let's say, 35 finished the race. And you can see the DNFs, they kind of start around that side of things, right? 25% data, another 25%, another 25%, 25%. Outliers are marked here. It's incredible. Someone at the age of 80 attempted 100 milers. Now, 100 miler. Now they didn't finish, but still attempting it. You can see on this side of things that someone was early 20s, and that's the youngest finisher. In 2024, the youngest finisher was even younger, which is typical, right? You don't have a lot of experience running 100 milers. And 2024 finishers, right? There's people a little bit younger than I am that finished. And then 25, 25, 25. And you can see oldest person looks like they did not finish, slightly a little bit higher here. But yeah, so I just thought this was a pretty cool thing to plot between the finishers and DNFs. It kind of shows like you're older, probably not as successful on this side of things, just slightly. But one thing to note too is it's a grueling event. It's 100 miles, right? And there's people that are in their 60s and 70s that are finishing this. You can see 60 years old. There's a decent amount, right? You can go over here to 2023 finishers. There's someone almost 70 years old that finished this event. But yeah, I thought it was kind of cool to plot that out now. And now what I want to do is have a violin plot. So we'll look at, all right, and now we're going to take a look at a violin plot. And this is going to be pretty easy, right? So we'll say sns.violin plot, and we'll look at 2023 first. We'll say data equals data 2023 finishers. We'll say x equals gender, see y equals race minutes, equals race minutes, inner equals quartile. And also duplicate this for 2024. That way we can take a look at both years. And run it 3, 2, 1. Run both of these. That's and the width of each curve on these are going to correspond with the approximate frequency of data points in the regions. So as you can see a little bit earlier, right? When we separate these out, they looked a little bit better on 2023. 2024, not so much, right? Female, you can see we have multiple peaks on this side of things, but it was almost like a uniform distribution. And you can see over here, there's a ton of skewing on the male side of things, right? A few fast runners, and then just like it's not good. And this was a little bit more normally distributed back in 2023. And just to show you guys again, right? This is 2023, right? And 23 female finishers. So we go back over here, right? You can see the normal distribution essentially, and then you can see the skewness on the female runners. And then we go back over here, right? Obviously not uniform, but it's pretty close. And then you can see the skewness once again. So really, like if you're painting a picture, kind of both these work. It just depends on like how you want to present it. And there's a few other data points that you could take a look at too. Like on this side of things, right? It might be assumed that like the average male runner is going to be faster than the average female, right? But then like you can even see like the 75%, 25, 50, 75% of males, right? We're at the 50% point for females. But then you look at 2024 and it paints a different picture, right? So you can see 25% of the males were right here, where that's like the 50% mark on females. And again, these races, and you guys are probably sick of it, but these races, there's a lot to them. It's not like a marathon. A marathon is predictable. 100 miles, it's not. A lot can go wrong. It's 4 marathons in a row. So what I want to look at now is a correlation side of things. So we saw a little bit over here that it looked like older runners struggled a little bit more and did not finish, right? Older and then somewhat younger, at least in 2024, which typically should be the case. Again, we don't have a lot of years, but I want to do a scatter plot and then also run a correlation between age and time. So let's take a look at that. So we'll see if there's a correlation. So correlation between age and time. And what we'll do is a scatter plot. So sns.scatter plot. We'll look at 2023 first, and then we'll look at 2024. So data equals data 2023 finishers, x equals age, y equals race, minutes, and let's add a hue. Why not? We'll say hue equals gender. And these plots are everywhere. Not really painting a picture. We'll get the actual correlation number a little bit later. I think it's after these. Yeah, we'll look at them after. But let's also look at 2024. All we got to do is change the 2023 finishers to 2024. It paints a better picture. And it does not. So what we're going to have to do on this side of things is run some correlation analysis. And what we'll take a look at on this one is the Pearson R. And yeah, we'll go through it. All right, so let's find the correlation now that we plotted both of these scatter plots. So the first thing I want to do is I want to test to see if age and then race minutes follow normality. And the way that I want to do it is through a Shapiro-Wilk. You could also use a QQ plot. There's a lot of different ways, but for simplicity, we'll do that. So we'll just say we don't need this other stat. We're just going to look at p-value. So we'll look at p age 23 equals, and what we'll have is here Shapiro, and then we'll have data 2023 finishers, and then just pass in our age. And we want to have this above 0.05, so print out that. And age, good, we're good to go. 0.744. Now, what we're going to do is the race. So I'm going to copy the code. I'll change this to race. So race. And we'll put race minutes in here. So let's change that to race minutes. And we'll print that out. So print out. And we get the value of what? 0.11. So close if we're using alpha at 5, or if we're using alpha 0.1, it gets close, but yeah, we're still should be good. So let's calculate our correlation. So we'll say core 2023, and then we don't care about the other value. We're going to use a Pearson, so Pearson R. And then in over here, we'll have our data age, so finishers age. And then up next, we'll have our finishers race minutes. And let's see the correlation. So what we do is print this out. And 0.23. So not really that good. And you saw the scatter plots, right? So let's take a look at 2024, right? Very little positive correlation associated with age and then also race minutes. So for 2024, we're going to follow the same process. So let's start off with our age, and we'll call this 24, and we'll just change that over here to 2024, and then we'll print out that. So print and 0.14. So unlike the other one, which was like 0.74, this is a lot closer to not following annual distribution. And let's look at the other side of things, right? Our race minutes. Now, our race minutes look pretty whack for 2024. And we'll call this P race 24. And print out that. P race 24. 0.01. Well, that is a problem because we can't use Pearson. Pearson assumes normality, and well, the race minutes in 2024 didn't follow normal distribution. So we're going to use Spearman's instead, and I've covered all these different types of correlation tests here on the channel, so you can check them out. But yeah, let's take a look at Spearman, and it's going to be a lot of the same code, right? So we'll just put correlation 2024, and then we'll put Spearman R, and then change this up to 2024, and we're good to go. And let's print that out. So print correlation 2024, and even worse, 0.1. Oh, kind of sucks. Can show a correlation between those, but regardless, at least you know, right? And that would be something to take a look at for this data set. And look, there's a lot of things that we could take a look at with this data set, right? I'm trying to put this all together in maybe like an hour to 2 hour video. So we're going to move on to some of the different types of tests. So let's call this test section. We'll set our alpha value to 0.05, which technically we could have done this before the correlations, but I wanted to plot these scatter plots and do the correlations. So we'll say alpha equals 0.05, and we should be good to go. All right, so let's start off our first test, and we're going to look at is a 2-sample z-test. Which, funny enough, when I'm recording this video, I haven't recorded my 2-sample z-test video yet, although the code is prepped, and so is the slides. But essentially what we're going to be doing in this one is we're going to compare 2023 to 2024, looking at the times. Now, I thought from just conversations with other people Again, people that either volunteered both years, they were pacing. 2024 was harder. And, I have a little bit of evidence behind that side of things. So first, the finish rate. Oh, I think first thing we did was the time, right? We do time first or do we finish rate? Let me look. Okay, so we looked at the time, right? 1726 versus 1809. That's over an hour difference between the 2 years. And then we looked at the median, which was even larger, right? 1732 to 1865. That's a 2-hour difference in time for the median, which is a lot. And we also looked at finish rates, right? 2023 had a 65%. 2024 had 54%. So I wanted to look at a statistical test on that side of things. And we'll use a z-test because technically we have more than 30 samples. And again, mentioning, right, there's no random sampling involved, just based off of we only have 2 years of samples and like we have 40 people that completed. Like it's not a large data set, but I wanted to go through all these different types of tests. All right, so first thing we have to do is extract some times. So what we'll do is race 2024 times, and we're going to see that's going to be equal to data 2024 finishers. We'll grab our race minutes. So race minutes like that. We'll do the same thing for 2023 also. So just grab that over here and take a look. I had 2 single quotes, so that's why that didn't work. Let me fix that over here for 2023. Let's also make sure that's 2023 over here. Great. And now we can take a look at the 2 samples. So we'll have a z-score and we'll have our p-value. So p-value. And this is going to be equal to our z-test. And we already brought in this import, right? And race 2024 times. Then we have race 2023 times. And then lastly, we're going to do a one-tail test alternative. And we're going to look at larger, right? The assumption is 2024 was a harder race, so you would have longer race times. And that's why we're only looking at the one side of the tail, and why we're doing alternative larger, right? We put 2024 first. So there's that. What's your prediction? What do you think? So let's take a look first at our z-score. So print, and we take a look at the z-score, and we get a 1.5 essentially z-score. And then we print out our p-value on this side of things, right? And well, our p-value is 0.06, which is interesting. Our alpha value is 0.05. So we're going to fail to reject the null hypothesis of the finishing times being different. But, if you had a different alpha value, if you had 0.1, you would reject the null hypothesis saying that the difference in both years, there's no difference, right? So just have this over here, right? If p-value less than alpha, reject the null hypothesis, the finished times are different. Else fail to reject the null hypothesis, no significant difference. This is going to tell you it's going to be no significant difference, right? And obviously I showed you guys there's more to look at a race than just the finish times itself, right? Just based off of people even finishing. And this is just looking specifically at finish times. So although we did see a difference in the mean and median, this test failed to reject. And we're going to jump now into example number 2. So example 2, we're going to use a paired t-test. So a paired t-test. And we're going to look at t-test. Look at participants that competed in 2023 versus 2024. Competed in 2023 versus 2024. And see if their times differ. So let's jump into this. And what we're going to have to do first is we're going to have to build out a merged data frame. And we're going to say merge data equals pd.merge. and let's put data 2024 finishers, then data 2023 finishers, and we're going to say on equals. And if you go back to our data cleanup, this is why I put full name, because we're going to join on the names. Now, I understand technically you could have a name like John Smith, and there's a John Smith that runs in 2023, and there's a John Smith that runs in 2024. Always possible, but that's how I'm working on this video. And you'll see that there's very few people that ran both years and completed the race, so we can take a look at those anyways. And also, since we have other data points like age and we have like city, we can always filter out if two people with the same name and they have different ages or different cities or different states. So we have that flexibility. That's why I'm joining on the full name. I wish there was like an ID for our participant, but there's not. So that's why I'm doing full name. And what we're going to do is we're also going to use suffixes to differentiate, because they're essentially the same tables, right? They're going to have the same columns. So we need to differentiate them, and suffixes allow us to do that. So we're going to put suffixes like this, equals, and we'll put 2024, and then we'll put 2023. So let's put both of those in there. Also, I recommend you put an underscore, so that's going to be after. Otherwise, it's going to look really weird. And we should be good. Let me just double check. Yeah, I think we're good. Great. And let's take a look at this new data frame. It's called merge data. We'll do a head of 5 because there only should be 3 rows if I remember correctly. And take a look. So we have 3. Let's take a look at our runners: Sage, Doug, and David. I actually ran with Doug like 5 or 10 miles, something like that, around the Buccaneers stadium and the Yankees spring training, well, now the Rays stadium. So let's take a look at this side of things. So we have Doug here, St. Pete, 100% confirmed he ran both years, because I was talking to him about it. And you can see St. Pete. Then we have Sarasota, 27, Sage. We jump over here, Sarasota, 26, right? So good there. And we have David, who's from Los Angeles. Age in 2024 was 25. And let's see if we have it again. Interesting here. That's interesting. Why is age in 2024 25? And then age in 2023 is 50. But you can see Los Angeles, California, and Los Angeles, California. You know, I didn't notice that the first time I wrote this tutorial or this video in general. I'm curious if it's like one of those cases where like his son ran the race. That's weird. I'm just gonna look really quick at UltraSignup. Just for this tutorial, we're gonna assume they're the same, but let's just take a look. I'm curious. Oh, we have UltraSignup over here. The name was David over here, David Paskey. Of course, it's not gonna show up now. All right, you see David Paskey here, 25. Yeah, that's weird because look at that. There's 2 David Paskeys. I just don't know. There's just not enough information. They both ran this race. I don't know. I mean, they're both from LA. It could be a junior situation and just not there. If there was a lot more records, I would drop it. But I just don't know. I mean, even looking at their times, 31 hours and 24. We're gonna keep it in the data frame. I wish there was more races or more context, because like I've had that happen with my name on UltraSignup, but I haven't had another Ryan Nolan, like you can see over here. Like there's other Ryan Nolans. This is me over here. These 5 races: Everglades, Chrome, Vero, Forgotten Florida. There. Back when I was in shape, and these have all been when I've been out of shape. But and there's another race that I did a 50K that's not in here. Just wasn't through UltraSignup, and run a few others that were like non-official, but regardless, we'll keep that in there. So we'll keep going with this test, but just note, I don't know 100% if this is the same person. I assume it is. Maybe there's a typo one of the 2 years that they're inputting their information. I don't know. They don't really verify ages and stuff like that. I mean, if you win, you win, right? Like, what is it? Bragging rights. There's no money involved with this stuff. All right, so what we're going to now take a look at is the time difference, because one of the things when we take a look at for the paired t-test is we want to make sure the difference can be normally distributed. Little caveat here, there's literally 3 samples that we're taking a look at. It's very tough to tell something's normally distributed at 3, so more likely we're just going to assume it's normally distributed for this video. But yeah, let me show you how you'd normally do it. I wish there was more, but maybe other people ran it, failed one year, completed the other year. It's always possible. We're going to look at merge data. We're going to look at and create a new column called time diff. And we're going to say this is equal to our merged data. And what we're going to take a look at is race minutes. Now, we're going to have 2 different race minutes. We have 2024, right? And we're going to subtract that from 2023. This is the suffix that we added at the very end, right? And this is why I said put an underscore. So we'll put both of these over here. We'll have race minutes 2023 like that. And here's our merged data. And what we're going to do really quick is run a Shapiro loop. And we'll say p race time diff equals Shapiro of our merged data time diff, like that is right here. Great. And then what we'll have next on here is just printing out our p-value. And we're hopefully having one that's greater than 0.05. I mean, there's other tests we could use, but I wanted to use a paired t-test for this video, and you see 0.32. So again, 3 samples, but regardless, we'll be jumping through this. All right, and what we want to do now on this side of things is take a look at our results. So a few things. Number 1, let's get our t-stat and p-value. P-value equals t-test rel. And then pass in our data. Actually, what I need to do first on here is, hold on 1 second because I skipped a step. What we need to do first is separate 2024 and 2023. So we'll say race 2024 equals merged data, and we'll have over here race minutes 2024, and then we'll do the same thing for 2023. So I apologize for skipping a step. We should have done that first. And also what we can do is we can take a look at some of the different data behind this, like what's the mean on these, what's the standard deviation if we really wanted to. We'll look at the mean. So we'll look at the mean on both of these. I'm not super concerned. So you can see 1530 for 2023. And then 2024, 1603. So our plus difference, 2024 is actually slower. And let's take a look at these individuals. So first one, Sage had 2337 in 2024. And then 2023, 1 day and 157, so 25:57, almost 26 hours. So that was an improvement. Doug over here, 1 day, hour 41, and then 1 day and 59 minutes. So he also improved. But then you have David, 2023, 1 day, 52 minutes, and then 1 day, 7 hours, 30. That's a huge difference. I just don't know what's going on with that record. And I feel like this is going to ruin our test. But I mean, do we want to really run a t-test on 2 samples? It is what it is for the video. And let's put both of these in here. I have a feeling we will not be rejecting anything. So we'll take a look. So let's print out our p-value. And what you'll see on our p-value side of things is it's 0.7. And we can write our if-else over here. And it's literally going to be essentially the same if-else statement, right? And what I say over here, if p-value is less than alpha, reject the null hypothesis. The paired finish times differ. Else, fail to reject the null hypothesis. No significant difference in paired finish times. And, well, you can see fail to reject null hypothesis, 0.7. Yeah, I mean, like I said, I didn't want to run it with just 2 samples. I just don't know what's going on there. My assumption is it's going to be like some type of father-son side of things. Maybe it's the junior, and it just never populated from their data set, right? That's why you have them both from LA. And or it's legitimately the same person, but they just put in the age wrong 1 year. But yeah, there is that example. And let's take a look at the next one. And what we're going to do for this next one is ANOVA. And we're going to look at by age. And well, it's going to be a little bit of work to set this one up because we're going to have to bucket the ages. What I'm going to do is bucket by decade. Sometimes races will do that to have different age groups, and they do age group rewards or not rewards, but awards and different things like that. So I think that's my plan, and we'll go forward with it. All right, so these next 2 examples, they're going to use either ANOVA or Kruskal-Wallis, and this is going to depend on Shapiro as well as Levine, and we're going to have to make some modifications to our data frame. Also, for these next few examples, I'm only going to look at 2024. So in the past ones, we've taken a look at 23 and 24, different things like that. But this one, we're only going to look at 2024. So first is going to be the ANOVA by age. So let's build out our age buckets. So what we'll say is we have data 2024 finishers, and we'll create a new column called age buckets. So make age buckets like this, age bucket, and let's start building that out. So we're going to say this is going to be equal to, and we're going to have our data 2024 finishers, and I'm just going to copy this, and we're just going to grab age, right? And then over here, we're going to say times 10, and then on the outside over here, we're going to have the as type. We're going to say string. And what this code does for us is we're taking our age, we're rounding to the floor, multiplying it by 10, and then we're adding as type as a string and adding that s over here. Okay. You can see we get a value over here, right? Our value, we're casting the value to a string, and we're splitting s. So we'll run that over here. And what we're going to do is, next line, we'll say race times by age equals, we'll have our data 2024 finishers. And what we're going to do is we're going to group by, and we're going to have our different age buckets. So we're going to group by our age buckets, by that. And then we're going to have our race minutes, right? Race minutes dot apply list dot values. Okay. And what we'll do on here is show you what this looks like. Okay, and next thing we're going to do is, if you want to see also, by the way, how this looks, let me just show you this real quick before we move on. And also making sure that this works, right? You can see 38, 30s. And that one code up there, right? 38 floor, right? Times 10. So 38, go to 3 times 10, 30. And that's why we have 30 and we add an S over here. 45, right? This will turn into 4, right? Times it by 10, 40, add S over there. So hopefully that makes sense on that side of things. What we want to do though is we want to make sure that the variance is going to be the same across all these different groups that we have. So we'll run a Levine's. So Levine is pretty easy. So Levine p-value age equals Levine. And we're just going to pass in all these race times by age. And let's print this out. You can make a giant if statement if you wanted to, but you'll see 0.56. I say that because we're going to run Shapiro in a second, but we're good on Levine. So now let's do Shapiro. So what I'm going to do is, since we're going to have a lot of different decades, right? 20, 30, 40, 50, 60s. And I believe there's 70-year-olds that ran this race and completed. Otherwise, we stop at 60s. I'll show you what we're going to do in a second. So we'll have Shapiro results. We'll probably put it into a dictionary of some sorts. So we'll say Shapiro results like that. Then we'll write a for loop. And we'll say for age bucket and race times in zip. And what we'll do next is data 2024 finishers age bucket. We'll grab that. And we'll grab unique. And we'll say race times by age. Okay. Then we're going to say stat and have our p-value equals Shapiro, pass in our race times. And also I should have a comment there. So for age bucket and race times, and that got rid of that error. Okay. And then we'll say Shapiro results of our age bucket equals, and we'll have stat p-value. Right. This should be Shapiro results, not Shapiro. I do have an issue over here. All right, guys, if you got the same error that I was getting and I had to debug it, I just restarted my session. I reran it and it works fine now. Not sure what was going on. I did notice that these weren't tabbed over all the way, so I did fix that, but I was still having errors even after running this. So just restart your session. You know, it does happen, and it's working. So now what I'm going to do is I'm going to display the results that we just got. So we'll say is for age bucket and stat and p-value in Shapiro results. So that over here, the items, print, and we'll do an F string. So we'll say age bucket, and we'll actually populate the age bucket. So age bucket like that. And then there's a comma. We'll have the Shapiro Wilk. Shapiro Wilk stat that we don't really care about, but it's all right. We'll put the stat there. And lastly, the p-value that we do care about. So p-value, and we'll put the p-value here. All right. Once again, I put bucket M instead of bucket comma. And you can see age bucket 30s, 40s, 20s, 50s, 60s. So there's no 7-year-olds that finished. And all of our p-values over 0.05. So we are good to continue our ANOVA. Awesome. So now what we can do is perform our ANOVA test. So we'll have F statistic over here and our p-value. And it's going to be equal to F one way, like that. And we'll just pass in race times by age. Age. We can print out our p-value. That, so print out our p-value. 0.52. And then let's write our if else, which I'm just going to copy in because I don't want to type it out. So if p-value is less than alpha, reject the null hypothesis. Differences exist between age groups. Fail to reject null hypothesis. No significant differences between the age groups. And fail to reject the null hypothesis. No significant differences. And I wanted to just finish off the ANOVA on the age side of things, just to calculate the mean, standard deviation, and kind of the number in each of these different age groups. So let's do that. We'll say for age bucket and group in data 2024 finishers dot group by. We'll have our age bucket. Right. Then we'll say print of an F string. Inside over here, we'll start with our age bucket, age buckets. We'll have mean equals of our mean, which is going to be in here, group, race minutes, that, the mean. We're going to round this to 2 decimal places, so 0.2f, that. And then we can also run our standard deviation. And we'll say STD deviation equals, let's give you the same thing here. Put STD like that. And lastly, let's say n equals, and we're going to put in here length, and just put our group. And I think that should be it. And I got that over here. And look at the mean, 1833, 1741, 1793, 1849, 2015. It's interesting because this kind of follows what's expected in 100 milers. Your 20-year-olds tend to be some of the slowest runners. It's just an experience. You improve a lot. 30 and 40-year-olds tend to be the best. You can see they performed better. 30s, like the peak age for ultra running. 40s, 50s, like 50-year-olds and 20-year-olds are about the same in this sport, which is kind of crazy to think about. And then 60-year-olds slowed down quite a bit. But there are 70-year-olds that do these type of races. I can't imagine running this at age 70. Kudos to them because way better athlete. Yeah, so that was our ANOVA on age groups. Now I want to take a look at ANOVA with locations. And I thought about how we could do locations on this, and I wanted to split it out 3 different ways. So first, I wanted to take a look at someone that was like on the course or just like slightly off the course. And I know all the different cities in this area because I grew up in the Tampa Bay area, and also I ran the course, so I know all the major cities that were on the course. And again, it started Ybor, went through Tampa, went through Oldsmar, Dunedin, then went through Clearwater, and ended in St. Pete. And there's a lot of cities that are kind of close into those areas, which I'll lump in. Also went through Palm Harbor. Um, Again, I'll lump those in. But then there's runners from Florida, right? So, maybe someone came down from Jacksonville or someone came up from Miami, or you have Orlando runners, right? So all those should be like classified as a Florida runner, but they're not on the course. And then we'll classify like everyone else outside of Florida as their own group, and we'll compare them. So let's do our location. And this one's going to either be ANOVA or Kruskal-Wallis. So Kruskal-Wallis by location. And we'll start by writing a location function. So we'll say DEF location status, and we'll populate the city and the states and get going. So what we'll say is if state equals Florida, right? Capital on both of these, and city in, and make sure I spell all these right, but Tampa, easy, right? Clearwater, St. Petersburg, Dunedin. Then we have, and I'm just looking at my notes over here because I don't remember everyone's in this data set. We had a few runners that were in Palm Harbor. And lastly, Largo wasn't on the course, but it's so close to Clearwater and Dunedin. We'll put Largo in here. And that will be for everyone that's considered on the course. And what we'll say is we'll return, oops, I accidentally typed on my second screen, but let me just go back over here. We'll return on or near course. So we'll say on or near course. Right. Then we can have an elif state equals Florida, right? Return, and we're going to call this Florida off course, right? And then we'll have an else, if I can spell, and we'll say return out of states. Return out of states. Great. So, all right, you're either on or near the course, you're Florida off course, or you're out of state. So now what we'll have to do is use a lambda function. And we'll say data 2024 finishers. And we'll have our location status. So location status. We're going to say this is equal to, and we have data 2024 finishers. We're going to apply a function, apply, right? And we'll say lambda row, because we're grabbing multiple things in here, location status. And inside over here, we have row city, row state, row state. And we'll say axis equals 1, like that. Give a small error. City should be capital. Yeah, city and state need to be capital. I'll throw those in there. So it grabs the city and state, right? And then runs this function that we built out. A little bit complicated with the lambda side of things. That's how you would do it. Now we have this in here, so we can just say data 2024 finishers. We'll have head 5. Okay. And you'll see, let's take a look at some examples. This is a Florida off course, Cape Coral, which is South Florida. You have Orlando, right? Florida off course. You have Atlanta, Georgia, right? Out of state. You have Sarasota off course, and the Lakes off course. Maybe we'll do 10. Right? We'll look at some others. All right. And man, all these are off courses, but well, that shouldn't be off course. It's St. Petersburg, so I probably butchered something on there, and you'll see there's probably a space. So let me fix that really quick. So it should be St. Petersburg. I think that's how there, because I should have the spelling correct. Let's see. And this is why we check, right? St. Petersburg on or near course. There we go. Perfect. So this is working correctly. Now, that's the only one that has a period in its name. So just depending on how the data is there. All right. Now we need to build out our different groups. So what we'll have over here is we'll say groups equals, we'll have data 2024 finishers dot group by. We'll have our location status, and we'll have race minutes, that's, and I'm going to combine a few different things into one cell next. So we're going to say on near course equals groups dot get group, and wait. Oh, I guess I should just take this out, on or near course. Grab these 2 and 3. Okay. Next is Florida off course. So Florida off course, and then just put over here Florida off, and then we have out of state, out of states, right? Of course, I have an issue. Did I capitalize off course? Yeah, of course I didn't capitalize the C on course. Just note, fix that. I'll fix it now. Let's just fix that really quick. Make sure that's there. All right. So I make sure capitalization. All right, I'm gonna restart my session. I guarantee it's gonna fix it. So restart session. I'm just gonna run all these again. All right, so we have all these groups now. Let's run our Levine's test. So we'll say Levine course p-value equals Levine. Pass in all 3 of these. So on or near course, then Florida off course, and then out of state. Great. And then let's print out this p-value. So print this out. And it's kind of low, but again, we have an alpha of 0.05. You're good to keep moving forward. Next side of things, what we want to do is get the Shapiro values for each of these. So p-value Shapiro on near course equals Shapiro, and we'll just pass in each of these one at a time. So we'll grab all 3 of these, 1, 2, and 3. We'll see Florida off course. What's that there? Out of states. Shapiro. Out of states. And we can print out all these also. So prints. And we'll just run a bunch of these all at once. I'd rather be more efficient than just typing out all these. Great. Great. All right, let's run these. 0.23. Good. Ooh. 0.04. We can't run our ANOVA because this fails, right? Florida off course does not follow a normal distribution. And let's just look at this last one, 0.15. So now we need to look at the Kruskal-Wallis, which looks at our median values. And really, I wrote a big if else statement. And I'll just paste it here for you guys. If Levine p-value less than 0.5, right? Shapiro on course, all this, right? Can't use ANOVA. And I changed my Levine name. I just put Levine course p-value here. So can't use ANOVA, use Kruskal. And look, can't use ANOVA, use the Kruskal-Wallis. So we're going to do that. So we'd have our h-stats, and then our p-value equals Kruskal. And then literally just pass these three in again. I'm just going to copy this because I don't want to keep scrolling up. And we'll just delete these at the end. So on or near course, or off course, and lastly, out of state. And we'll delete those there. Great. And what we can do is print out our p-value. So print out our p-value, this side of things, and 0.26, right? And because of that, we're going to use this over here. No statistically significant difference between the different groups. And what I also wanted to do is just show you how these different groups looked on both the median and mean side of things. So we'll say data 2024 finishers. We'll do a group by. So group by, we'll look at location status. Look at race minutes, and then we'll do an ag. So we can look at both the mean and median. So look at mean and median, like that. Right. Of course, I misspelled location status. This video is probably close to 2 hours already. So you can see the mean 1772, 1930, 1791. It's interesting. On or near course is the slowest on the mean side of things. I get it though. If you're local, you might want to just run that race versus like someone that's out of state or off course. You're traveling there. So you might be a little bit more dedicated. But I thought it'd been a little bit closer because on course, right, you can literally train in the environment you're going to run in. I even traveled down to Tampa to run in a few of these different spots before, and I've ran in a lot of the spots or been to the spots. But we take a look at the median. It's a lot closer. You can see off course is 1865, whereas on or near course is 1975, and out of state is 1844. And again, like when we saw our 2024 results, right, it was left tail, and you can see the mean on this side is less in each of these instances, where the median is more into the right. Those people that ran the race really, really fast, they pulled the mean down. So there's that. And lastly, we're going to take a look at a chi-squared example. All right, and our last example is going to be a chi-square test for independence. And we're going to look at a categorical variable. So categorical variable, and that's going to be finishing the race. And we're going to look at 2023 versus 2024. So let's build this out. So we're going to say finish 2023 equals length, and we'll have data 2023 finishers, right? And what I'm going to do is copy this and put that for 2024. And then we're going to put DNF 2023 equals length data 2023 DNF. We'll copy that again. Do that for 2024. Just double check 2023. Yep, we are good there. And then we're going to build a contingency table. So contingency table equals np.array. and in over here. Else. And if you're not familiar how to do this, no worries. I have my linear algebra videos coming out shortly after the stats series. Well, I already have some of those linear algebra videos out, but I'm building out that full playlist. So we'll finish 2023, DNF 2023. We're going to just copy this, do the same thing for 24. All right, so that's our contingency table. Then we can do our chi-square stat, chi-square p-value, degrees of freedom, expected equals chi contingency, and pass in this contingency table. And let's take a look at our final results. So we can print out our chi-square statistic, 1.69, and print out our p-value. You can see it's 0.19. So once again, we fail to reject our null hypothesis. And I think this is a good ending spot. And we'll roll out to the outro of this tutorial. Or not tutorial, but kind of project. We accomplished a lot. And if you made it this far, I appreciate you sticking it out. We did a lot of coding today. We'll reach the end, and I just want to thank you guys for checking out this project. I thought it'd be a good way to tie together ultra running, which I really like, as well as a good longer statistics video for the channel. And if you guys enjoyed it and you found it a little bit valuable, make sure to subscribe. And also, if you want to learn even more about statistics, I have a full playlist. I'll link it down below and put it on at the very end of this video, but I'm going to continue to build it out. I think right now there's like maybe 40 to 50 videos, but I'll still try to upload like 1 or 2 statistics videos every single month, eventually trying to get the playlist to 75 to 100 videos. So make sure to keep checking that out. And if you weren't familiar with any of these type of tests, I have videos on all of them on the channel already. I'm going to put them before this project in that playlist. So thanks again, and I'll catch you guys in another video.